Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will obtain the posterior distribution of mu, where mu represents the mean of a normal process where the variance sigma squared is assumed to be known. We will do this for a sample of size 1, and we will consider a normal prior for mu. Okay? Well, let's begin. So, as I said just a few seconds ago, right, the likelihood we will consider is the likelihood of a single observation. Later, we will see that we can easily extend this to the case where the likelihood that we are interested in is the likelihood of a sample of size n. Okay? So likelihood of a single observation. So we know that the PDF, the probability density function of a normal, is going to look something like this. So given that we have the parameters mu and sigma squared, the mean and the variance respectively, so the PDF looks something like this, right? We have a normalizing constant that is given by 1 over sigma times the square root of 2 pi. That's just that normalizing constant. Then we have e to the power negative 1 over 2 times sigma squared and then times y minus mu there we are, squared. Okay, so as we mentioned at the beginning, we're assuming that sigma squared is known, then we could rewrite this expression like this. The likelihood will be proportional to, note that that normalizing constant could be absorbed by the proportionality symbol, and then the only unknown parameter is mu, right? Okay, so this will be the likelihood that we're going to be dealing with. Okay, so by the way, some places you could see the following notation. Instead of e to and then this exponent, maybe you will see something like this: exp as in exponential, and then you will see that exponent. Okay, make sense? It's just notation. This is the same. Okay? Okay. So, next, the other ingredient, since we're going to be analyzing this single observation coming from a normal process with mean mu unknown and variance sigma squared known, from a Bayesian perspective, we need the second important ingredient is our prior. Okay, so also, as we said, our prior will be a normal density for mu. Okay, so our prior normal density for the parameter of interest mu. Okay, so since we are considering normal, right? So let me borrow this. Okay, let me borrow the expression of the likelihood, and then we're going to change it accordingly. So the notation that we use for the prior is just p of mu. In this case, that's a parameter of interest, and then we're going to have m will be our prior mean, and we're going to have s will represent, if you want, we could use s or s squared. If we use s squared, this guy would represent the prior variance, and then s would be the prior standard deviation, right? Okay, so the normalizing constant would look like this. Instead of sigma, we will have s. The variable is no longer y, but mu, and the mean will be represented by m, right? So that's the prior that we're going to be considering for mu. A normal prior with mean m and standard deviation s, or variance s squared. Okay, and again, if we absorb the normalizing constant, because this guy here doesn't involve the parameter of interest, in this case mu, we could write down the prior using the proportionality symbol like this, just this guy here. Okay, and using that notation exp, it would look something like this. So e to that power, right? Make sense? Okay. So now we know that the posterior, right, in plain English, well, first let me write it down like this. Remind you that our posterior is proportional to prior times likelihood. Okay, so the notation that we use for our posterior, in this case it would be probability of mu given our single observation y. We know it's proportional to prior times likelihood. Oops, not what I want. Times likelihood. Likelihood is y given mu. Given mu. There. Okay. So it's going to be proportional to this, right? I don't like how that looks. I don't know why it doesn't look like the other one. Okay, let's leave it like that. It's not such a big deal. times the likelihood. Okay, let me see if I can make it look bigger, like this one. For some reason, you know, the size doesn't look the same. Let me just copy paste this one and modify that. I want it to look bigger. Okay, so now we have s squared here. We're going to have mu, and we're going to have m. Okay, okay, that looks better. It's easier to see, right? Okay, so we have prior times likelihood. Okay, so we know that this guy, right, we could combine the exponents of these two exponentials, right, and it's going to look something like this. It's going to be a single exponential to the power. We're going to have first this one plus this one here, right? And note that we have a common factor. We have as a common factor negative 1/2. Okay, so let me pull that guy out. Okay, let me rewrite this as follows. So we have mu minus m squared divided by s squared, right, plus, and then we're going to have y minus mu squared, and here we will have sigma squared. And we said that here we will have as a common factor negative 1 divided by 2. That is affecting both of them, right? Makes sense? So just a little bit of algebra, right? We're pulling out that negative 1/2, that's a common factor, and then we have mu minus m squared divided by s squared plus y minus mu squared divided by sigma squared. Agreed? Okay? Okay. So now I want you just to pay attention to this guy. Well, to these two guys, right? So it's going to be just, let me pull this guy out here, because I want to make sure that you're looking at like this. It's a common factor, right? This negative 1/2 multiplies this guy and this guy as well. Okay? Okay. So, as I was saying, what we're going to be doing here is you're going to pay attention to this. We're going to expand this. Okay, we're going to do it elsewhere. We're going to need more room. But that's the idea. Let's do a little bit of algebra with that part of the exponent. So, first, note that a common factor, a common denominator, right, would be s squared times sigma squared. Okay? So let's do that. S squared times sigma squared would be a common denominator. Then, if we're going to do the sum, right, what we're going to have here is, instead of this guy, It's going to be that guy multiplied by sigma squared plus this guy will be multiplied by s squared. Okay? Agreed? Right? Okay. So now let's do a bit more of algebra. Let's see what we have here. We are going to have mu squared, right? Then we're going to have minus 2 times mu times m plus m squared. Okay, so we no longer need that exponent there, right? Just, you know, just expanded this, mu minus m squared. Let's do the same with this one here. So we're going to have a y squared 2 times y times mu plus mu squared. Agreed? Okay. Now what we're going to do is combine the terms that have to do with mu square, right? Then those that have to do with mu, and those where mu is not involved at all. Okay? Let's keep going. So, note that, let me copy paste this. Let us start with those that have to do with mu squared. Okay? Let me just have something like this. Okay? First, let's pay attention to terms that have to do with mu squared. So we have sigma squared times mu squared, right? So we have that sigma squared. Okay? The other one that we are going to have is s squared times mu squared. Okay? So we could do something like this. So sigma squared times mu squared would be this, plus s squared times mu squared. That's the other one. And there's no other term that involves mu squared. So we're done with that one. Okay? Now, let's see. We have 2 times mu. Okay? We have 2 times mu here. Let's now try and just put together those terms, right? So we would have sigma squared times negative 2 times mu times m, right? So what we have here is sigma squared times m. That takes care of that term. Agreed? Now plus times minus, that's this guy, and then we have s squared times y. Agreed? And we're done with those terms that have to do with mu. Okay? Let's do the last 2 terms. It would be sigma squared times m squared. Okay? So we have sigma squared times m squared plus s squared times y squared, right? This one doesn't have to do with mu at all, right? So s squared times y squared. Good? Yeah? No problem? Okay. So, now, what we're going to be doing is note that this is the same as mu minus m squared divided by s squared plus y minus mu squared divided by sigma squared. So let's substitute this into the expression that we had here. Okay, so let me copy that here, and we're going to have this inside those curly brackets. Then outside we have that negative 1/2, and then we have that exp, right? And the proportionality symbol. Okay, are we good? Yeah? Okay, now what I want you to see is this. We could express this. We're going to break down this exponent into two parts, right? Note that since we're assuming that sigma squared is known, this is going to be a constant, right? And it doesn't involve mu. So we're going to have a product. This exponential we're going to express as a product of two exponentials. This guy and this guy involves mu, right? So that's one of the exponentials we're going to consider. The other one, it's going to be exp to the minus 1/2 times this, right? The third term here. But that one doesn't involve mu. So we're going to be able to absorb that guy, you know, using the proportionality symbol. It's a constant with respect to mu. Okay, so let's do it. So this is the same as the product of the following two exponentials. That times this. Okay, so for this one we get rid of the last term, right? And for this one we get rid of the first two terms. We're just breaking down that into the product of two exponentials, right? Just like that. Okay, can you see? That's what we're doing. Okay, this one here, the last one, this guy doesn't involve mu, right? It has nothing to do with mu. And then what we can do is, you know, this is proportional to just this. Okay, we ignore this one because it doesn't involve mu. Okay, okay, now another step. Note that what we have here is e to the negative 1/2 times something. If we had something, if we had an expression, a function that looked something like this, e to the negative 1 divided by 2 times something times y minus something squared, we would have the kernel of a normal, right? And so we almost have something like that. But the thing is that we need to have here some sort of a squared, right? So we will need to do a little bit of algebra to make it very clear that what we have here is deep down the kernel of a normal. Okay? So now what we're going to be doing is we're going to be playing around with that exponent that we have here. So first, before we play around with that exponent, note that what we could do here is we could just factor out that term. That's, a common term, right? Just factor it out, and then let me just keep the numerator. We no longer need that fraction. Okay, so same thing, right? I just pulled that out. Okay, so we have e to the negative 1 divided by 2 times s squared times sigma squared. Now, if we could re-express this as something minus something squared, we would have the kernel of a normal. So that's the idea. So let's do a little bit of algebra with that exponent. Okay, let me copy paste this and do that algebra somewhere else. Okay, so that's what we have, right? Okay, note that this is the same as this, right? We could just factor out this guy. And if we did that, we would have mu squared minus 2 times mu and then we would have this divided by sigma squared divided by s squared. Okay? Can you see that? Yeah? Agreed? I'm just factoring out sigma squared plus s squared. So this one would be sigma squared plus s squared times mu squared. That's the first term. And then, since I am factoring out this guy, then I have to multiply by this, and then I end up with what I want. Okay? Those two expressions are equivalent. Okay. Now, note that what we would like to have here is complete the square. Okay? So this would be the first term. Mu minus something squared is what we want. So mu minus, this would be the something that we need squared, okay, to complete that square. So I'm going to be adding a 0, okay? So if we did plus that, the whole thing squared, minus that, I'm just adding a 0, right? I'm not doing anything wrong. Okay, this minus this, that's just a 0. But the beauty of this is that mu squared minus 2 times mu times this plus this squared, we could rewrite as just mu minus sigma squared times m plus s squared times y divided by sigma squared plus s squared. Make sense? So that would be the next line, right? So what we have here is, let me copy that one here. again, what we're going to have here is mu minus that quantity squared. And here let me use curly brackets to make a difference. Yeah. Oh, come on. Okay, better like this, right? Okay. So anyway, mu squared minus 2 times mu times sigma squared times m plus s squared y divided by sigma squared plus s squared plus that whole thing squared is the same as just that term here, mu minus this kind of ugly looking thing, the whole thing squared, minus this guy, right? Okay. So now we are in business. Okay, so we're going to plug in this, right? Instead of using this, we could substitute that by this. Okay, that's exactly what we're going to be doing next. So let me copy this and go back to this part here. So instead of this, right, we will have this inside our curly brackets, right, and we will have this exponential, right? So note that actually this guy here, right? Now this is a common factor for all of them, right? So let me place it here. Okay? So this is the same as what we had here, and that's why we just substituted that. Okay? But that's a common factor. Let me place it here. So it looks nicer that way. Okay? Now, next step. We're almost there. We said that basically the main goal was having something that looked like e to the negative 1 divided by 2 times something squared times mu minus something, the whole thing squared. We already have this guy here. What about this guy here, this term on the exponent? Note that we're assuming that sigma squared is known, right? So this is going to be just a constant. M is known. That's a mean, that's a prior mean. S squared is the prior variance. Y will be known. Once we have our observation, it's also a constant. So this is just a constant. So if we express this exponential as the product of the following two exponentials, the second one, the one that has to do with this one, is just a constant. So we could absorb that by the proportionality symbol, right? Okay, so let's just do that here step by step. So what we have here is an exponential times another exponential. So the first one, we don't want this one here. For the first one, for the second one, we don't want this one. Okay? Makes sense? So we have this is the same as this exponential that has to do with the first term times another exponential that has to do with the second term. But this one, note, is a constant with respect to mu. So what we have is that our posterior is just proportional to the first exponential, right? We're almost there, okay? Let me rewrite this as follows. Note that e to the negative sigma squared plus s squared divided by 2 times s squared sigma squared times something is the same as this. Let me place a -1 here, and let me just borrow this guy and place it here. How's that? These two are, you know, equivalent. If you do the algebra, then you would be multiplying by this guy here, right? So it's just a little bit of algebra with that exponent that we have here for that exponential. Why do I care about that? Let's see the expression of the PDF of a normal with mean mu and variance sigma squared, right? If we ignore this constant, the normalizing constant, the kernel looks like this: e to the -1 divided by 2 times something squared times y minus the mean squared. Okay? So we have -1 divided by 2 times something squared. Guess what? This guy is our something squared. Okay? And then we have mu, and note that this guy is our posterior mean. So it's a function of mu, right? Mu given y, right? So what we have is our mu is here minus something squared. So this guy is our new mean, and this guy is our new variance. So what we have here is that the posterior, from this expression, from all the math that we have done, we have shown that the posterior distribution, when you consider a normal prior for mu, well, the posterior is also normal, and the new mean m star, right, is given by that expression, and the new variance, the posterior variance, is given by that expression. Okay, so let's write that down, and in the near future we're going to be using those expressions for the posterior mean and the posterior variance to come up with something called updating rules. Okay, so anyway, so our posterior mean has a normal distribution, with, let me call it mean or posterior mean, let me use m star to refer to the posterior mean, this guy, and we are going to have our posterior variance. It's going to be s squared, well, s star squared, right? It's going to be this guy here. Right? Okay, so let's summarize what we did. So we considered a likelihood coming, well, a normal likelihood, right, for a single observation, right? So with this normal likelihood, we are going to be analyzing that normal likelihood with a single observation using a normal prior, okay, for mu, because we're assuming that sigma squared is known. And after doing the math, right, what we realized is that the posterior distribution, if you will, the conditional probability of mu given y, the posterior has a normal distribution, and the new parameters for that distribution are mu star is given by sigma squared times m plus s squared times y, where m represents the prior mean and s represents the prior standard deviation. Sigma squared is the variance of the process, of the normal process. We're assuming that guy to be known. And the posterior variance, s star squared, is just s squared times sigma squared divided by sigma squared plus s squared. Okay? So later we're going to suggest a way of being able to memorize these formulas, or an easier way of seeing how we're combining the information coming from your prior and your likelihood. Okay? So, and we're going to come up with what we call updating rules. Okay? But, well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.